This is a calorimetry problem with a phase change involved. And there's an uncertainty about whether or not all the ice melts. So for this kind of problem, I find it best to kind of separate it out. So let's look at how much energy each step is going to take. So to heat up the ice to 0, it's going to take delta Q of 0.650 times the specific heat of ice times 75. Okay, and that's 101,887.5. To melt the ice once it is at 0 degrees, so we turn the ice into water, which is still at 0 degrees, it's going to take delta Q of 0.650 times 333,000, the latent heat of fusion for water. And that's 216,450 joules. Okay? Now, so that's how much energy is going to be, that's how much energy it's going to take for the ice. Now let's check out to cool the water that already exists, and that's hot, and the aluminum down to 0 degrees. Okay, so there's two different waters in this problem, right? There's the ice that could turn into water, and then there's the water that was already in the pot. So the delta Q to cool that down, well, let's see, so let's start with the aluminum. There's 1.2 kilograms. It has a specific heat of 900, and our final temperature is 0, and the initial temperature is 82. For the water, it's 4186. It's the specific heat, and delta T is also minus 82. So that's minus 88,560 minus 85813, which is minus 174,373 joules. Okay, so let's check it out. So if we compare this number to this number, right? So let's start with that comparison. So the magnitude of 174,373 is greater than 101,887. So the ice heats up to 0 degrees Celsius for sure, because the water can, as the water cools down to 0, the ice heats up to 0, and the water still has about 73,000 joules left over. Okay. However, if you look at the total delta Q to heat and melt the ice, that's 318,337 joules, which is way more than the minus 174, right? So since 337.5 is much greater than the 174,373, I'm not going to, these absolute value signs are a little bit confusing, so I'm not going to bother with them. I think you're getting the idea of what I'm doing. Then that means that not all the ice melts, right? Because, so there's plenty of heat dissipated in the water and the aluminum to heat the ice up to 0 degrees, but not enough to melt the ice completely. So not all the ice melts. Okay, that means that the final temperature of the system is 0, since the ice partially melts, and we must find the mass of the ice and treat that as our unknown. Okay. Okay, so our calorimetry equation, it looks like we're starting over from scratch, but I promise you we're not. We've already done a lot of the math that we need to do. So delta Q for the ice, we already know that to heat the ice up to 0 is 101,887.5. And then to melt the ice, it's going to take the mass of the ice that melts times 333. Okay, so this part right here is delta Q for the ice. Delta Q for the water and the aluminum, we already calculated that. For water and aluminum to cool down to 0, that's minus 174,373. Okay? And so now I just have the mass of the ice times 333,000 is equal to 72,485.5. That's how much energy you've got left over once the water cools down to 0 and you heat up the ice to 0. And if I solve for the mass of the ice, I get 220 grams, or 0.220 kilograms. Now that makes sense because you have 650 grams of ice total, so the mass of ice that melts is less than that, which is what we expected. Not all the ice melts.